Good afternoon, everyone. Thank you for joining us for today's webinar. My name is Luis Vila. I'm a structural engineer at GM2 Associates in Glastonbury, Connecticut, and I will be presenting the load rating of a steel composite girder bridge. I will start with a brief introduction about the bridge and the city where it is located. Then I will move on to the modeling aspects of the different components of the bridge. Then I will present the construction stage and live load analysis that we conducted to perform the load rating. Then I will go into the actual load rating process and then finalize with the analysis of an expansion joint on the live load. The bridge is located in the state of Connecticut in the United States. More specifically, it's in the city of Stamford, which is on the shoreline of the Long Island Sound and right on the border of the state of Connecticut with the state of New York. And just to give you a frame of reference, the city of Stamford is about 30 miles away from New York City. Here we have a satellite view of the bridge and the location. So here we have I-95. The bridge carries I-95 over a few local roads over here and all over Metro North Railroad. So this railroad over here, it's the New York-New Haven line of Metro North. Here we have the downtown Stamford and the financial district. The bridge limits are shown here by this red lines over here. And adjacent to the bridge, we have another bridge, which is actually an off-ramp of I-95 southbound, which provides access to downtown Stamford and the financial district. Bridge 32 was built in 1958, and since then it has undergone a lot of renovation projects. And this work includes joint replacement, substructure strengthening, bearing replacement, and widening of I-95. And actually, if you take a look over here, this is the original width of the bridge. And as you move towards the right in this picture, you can see the roadway becomes wider. That was part of a renovation project. And that's actually something that we had to consider when doing the load rating in Midas, as far as the materials used in the original construction versus those used in the widening project. And that was something that Midas handles very easily within the software. This bridge was recommended for rehabilitation due to the condition of the deck noted during the last inspection report a few years ago. So we are conducting the rehabilitation study, and as part of that rehabilitation study, we are conducting the load rating. This is the span configuration of the bridge. Basically, we have 17 spans. We have a joint that runs along the length of the bridge, with the exception of this main span over here. And as you can see, we have a few non-typical geometry of the bridge. Here we have, for example, a trapezoidal span, and we have a few triangular spans along the bridge. So due to this complex geometry, and based on previous experience using Midas for complex load ratings, we gave our recommendation to Connecticut DOT to rate this bridge using Midas. And also Midas, it's an approved software for Connecticut DOT. As I mentioned, the bridge is composed of 17 spans carrying I-95 over Metro North and local roads. The total length of the bridge is just over 1,000 feet long. And besides the unusual geometry, 16 of those 17 spans are your typical steel composite girder bridge. The main span, which is the one over the railroad, it's a little bit different. Here we have composite and non-composite floor beams, and also we have two steel through girders. For the purpose of today's presentation, I will be focusing on the main span and the work that we did over there. So the main span, it's span 7. Here we have the framing plan. It's a 200-foot span. The direction of the traffic, it's as shown over here for the southbound traffic and the northbound traffic. This is the location of the steel through girders. And just to give you an idea of the dimensions of the structure, the depth of the through girders, it's around 11 feet. Then we have our composite and non-composite floor beams that are running in a skew angle with respect to the direction of traffic. And here we have the floor beams are supported at this end by pier number 6, and then over here by pier number 7. Then the other ends of the floor beam, it's connected directly to the through girders. So in addition, we also have a diagonal expansion joint that runs along the length of this floor beam. And actually, all the floor beams in this span are composite design, with the exception of this floor beam that it's located directly below the expansion joint. So I will later in the presentation I will talk a little bit more about the expansion joint, what's the actual configuration there, and how we model that within Midas. In terms of defining the geometry of the bridge, Midas provides different options. Probably the most convenient for cases like ours, where you have a complex structure or a complex geometry, it's the option of importing your geometry from a MicroStation or AutoCAD file. Midas also provides the bridge wizard, which covers, for example, steel composite bridges, pre-stressed concrete, and other types of bridges. And this bridge wizard, as James was mentioning during the introduction, it's really helpful to model structures, including the loads applied to it, very quickly. The other option that Midas provides for the definition of the geometry, it's to define the actual geometry inside Midas, and in that case you will need to define the nodes within Midas and then connect those nodes with your elements. So I will start with the modeling aspects of the different components of the bridge. For the steel composite girders, we have a composite material which Midas defines as an SRC, and then the section, for the section properties, we have again a composite section. Here you can select different types of composite sections, for example, steel eye or eye-shaped girder, as we have in our case, or a steel top girder, and other types of section types. So for the section module, the deck, it's only being considered to determine the stiffness properties of the section. And what I mean by this, it's that we are not considering the weight of the deck within this composite section. So to do that, we set this ratio here equal to 0. Now to consider the weight of the deck, what we're doing is we are applying the weight of the concrete deck as a distributed loads over the floor beams. And also, Midas allows you here to consider the effects of creep and shrinkage based on the modular ratio. For the modeling of the steel through girders, here what we have, we have a built-up section. So the through girders are composed basically of 2 wet plates and then 6 plates for the flanges, and that will be 3 on the top and 3 for the bottom flange. and also a pair of longitudinal stiffeners. To include this in our Midas model, we used a tool that's built in within Midas, and that's called the General Section Designer tool. And what this tool allows you to do is import your shape from, again, either a MicroStation or AutoCAD file, just as you can do with the bridge geometry. Now, because we have to consider the stiffness properties of the section for the analysis, then Midas also calculates the section properties of the built-up section. This is a view of how the General Section Designer tool looks like. So it's located within the Tools tab in Midas, and then this is what the section looks like once you import that into the General Section Designer. Once you have it inside this module, you can link this to Midas and then import your section. And this is what it actually will look like inside your Midas model. Also, once you're in your Midas model, you can also pull up the table with the stiffness properties calculated by Midas. For the concrete deck, we are using dummy elements. And again, since we are considering the weight of the concrete as a distributed load on the floor beams, we assign the material here as a weightless concrete. So here we select the concrete material, and then we set the weight density equal to 0, so that the weight is not accounted for when we use the self-weight option in Midas. The purpose of this dummy elements is to connect the floor beams and then provide the transverse distribution of the composite dead loads and the live loads. So the live load will be applied directly to the dummy elements, and then based on the stiffness of different members, the dummy elements will distribute this live load to the different floor beams. So, okay, here we have a closer look of the diagonal expansion joint. And this will be our non-composite floor beam. So the detail here, it's in this figure, the left side of the deck. It's even though the floor beam is a non-composite design, the left side of the deck, it's firmly attached to the top flange of the floor beam. The right side, it's just sitting on top of the top flange, and then it is freely able to move over that top flange. So to model this within Midas, we use a series of links. And if we take a closer look, this will be the side that it's firmly attached to the top flange. So in this case, we use rigid elastic links to connect the dummy element to the floor beam. Now on the right side, what we did is we had here we have the insertion point of the dummy element. So we created a node directly below the dummy elements, and then joined those two nodes with a compression only link. So essentially what this allows us to do is to transfer shear from the deck to the floor beam, but then it will allow this dummy element to freely move in the horizontal direction, and also it will not have any shear or any tension force being transferred over here. So once we have that, then we connect this node to the floor beam with a rigid elastic link. Now for the construction stage analysis, we carried the construction stage analysis to determine the non-composite loads and the composite loads for the load rating. And this is one feature that I really like about Midas, and it's the visual display during the modeling. I think it really allows us to make sure that we are modeling the bridge correctly, and that we are considering the the correct section properties as we model this, and I will talk about that in a minute. So to define the composite section for construction stage, and then determine when we want that section to be non-composite and when we want it to be composite, we have to create a composite section for construction stage. And basically here, what we do is we select at which stage the steel become active, and at which stage then we have our concrete becoming active. And what I was saying about the visual display of Midas, it's, for example, here you can see once you define your composite section for construction stage, you can see here that in the non-composite stage, you have only your steel. So in the model, you can go through the different construction stages and visually verify that this is the case for all the sections that are intended to be non-composite at that stage. Once you have your composite section activated, then you can see over here the lines representing the concrete deck. So we have a steel-only construction stage. Then we have our concrete pour, considering the weight of the wet concrete still under non-composite action. And then finally, our composite section is activated and our dummy elements are included. And then hit to this stage is the one that we add the composite dead loads. For the live load analysis, we carry the live load analysis for the design loads and then also for the Connecticut permit and legal loads. And in Midas, once you set your lane definition, Midas allows you to have two options to how you want to carry your live load analysis. And basically the default option is that your truck will be placed in the center of your traffic lane. It also has an option that is called traffic lane optimization. And what this option does is that it moves the truck transversely within the lane. So in addition to the default option, it also considers the case when the truck is shifted towards the left of the traffic lane and also towards the right of the traffic lane. And then for the results, it gives you the most critical of these three cases on an element by element basis. So for each element, it gives you the maximum demand loads out of these three cases. For our lane definition, we have both forward and backward moving load. We have 7 lanes defined, four of which are northbound lanes, and then we have 3 southbound lanes. Once we carry the live load analysis, we have here the moment diagrams for the design load, and this it's a good point to verify that our bridge has been modeled correctly. For example, in a simple span bridge like this, then this is the type of moment diagram that you would expect. And here we have our steel through girders picking up the largest moment. And if we look at the floor beams only, then we have our non-composite floor beam picking up the largest amount of moment. For the live load analysis, we can also take a look at the displacement results. Here we show the displacement results for the design truck. And again, a good opportunity to verify how if the model it's behaving as we expect, and it's being modeled as it's being modeled correctly. So here we can see actually by the sudden change in the slope of the dummy elements from this point to this point, we can see that there is a discontinuity in the bending stiffness at that point, and that's actually where our our expansion joint it's located. For the load rating, we carry the load rating for strength, service, and fatigue limit states. So essentially, to conduct the load rating within Midas, what you have to do is define your rating case for according to your limit state. And once you select your code and your limit state, these load factors will be automatically generated by Midas. If for some reason you need to use different load factors, you also have the option to modify these different factors. Now, I will not go into too much detail for the strength and service limit state, because those are more commonly covered. I will go a little bit further into how Midas calculates the fatigue rating and what's how the typical results look like. So for the fatigue limit state, essentially what we have to check is whether our fatigue stresses are larger or are smaller than the fatigue threshold based on the fatigue prone detail. So Midas performs this check over here. If your fatigue stresses are less than your fatigue threshold, then the detail checks okay for infinite life fatigue. If it doesn't, then you will need to calculate the finite life fatigue or the remaining finite life based on this equation. So there are a few other parameters that needs to be defined to conduct the fatigue load rating in Midas. So in the rating tab, you'll find the fatigue parameters, and that's where it will allow you to select your fatigue category, your single lane ADTT, and your number of cycles. And this will all come from the LRFD equations. So in addition to that, Midas gives you the option to input the results from a diagnostic test or a load test. So here you can input the result from that test. Typically, it's probably not done for most cases. So even though if you don't have a test result done or conducted, you still have to input some value over here in order to be able to carry your load rating. So if you don't have any load test conducted, then you can select user input, and as per the manual for bridge evaluation, then select a factor of 1. This is what your typical fatigue results look like. So here you're going to have your fatigue threshold, again on an element by element basis, based on how you assign that for your fatigue prone detail. And then here we have the stress in the top and bottom flange for the fatigue loading. And here then Midas is giving you the rating factor. And again, if the rating factor it's less than 1, then the finite fatigue life will need to be computed in a separate spreadsheet. However, Midas does give you the fatigue stresses, so you can export this into your spreadsheet to calculate the remaining fatigue life. So once we go to the expansion joint, here there were a few conditions noted during the most recent inspection report. And obviously, this is a not so typical case that you have an expansion joint running along the length of a floor beam or a girder. So as usual, expansion joints tend to leak water with the de-icing elements. So we had a corrosion of the floor beam or underneath or below the joint. we have corrosion of that floor beam due to the water leakage. And also, it was noted that the bottom part of the deck was damaged due to repeated impacts against the top flange. So it was noted that the deck was pumping under live load and hammering constantly the top flange. So here I have a few pictures of a field inspection that we conducted to assess the situation of the joint and the non-composite floor beam. So this is the main span over the railroad. You can see that over here. Actually, there's a train coming over there, and here you have the cables for the catenary system of the railroad. Then here you can see the planking that was installed for the inspection of the floor beam and the joint. And actually, from here, you can see this is our non-composite floor beam, and you can see that adjacent floor beams are pretty much in perfect condition. When you compare that to the non-composite floor beam, you can see over here the corrosion caused by the water leakage. This is on top of the planking that I just showed you. So this will be a bay in between the two floor beams. And here we have the two sides of the non-composite floor beam. So we have over here the south side, which is where the deck is firmly attached. As you can see over here, the deck is firmly attached to the floor beam, and you can see it's the floor beam is in very good shape over here. Also the hunch and the deck, besides this small spall over here, the deck is in very good condition on this side. Once you go to the north side, which is where the deck is free to slide over that top flange, you can see the level of deterioration over here, corrosion on the web stiffeners, the web and the flanges as well, and also damage to the hunch over there. Here we have a closer look of the expansion joint below the deck. Again, deterioration and corrosion here of the top flange, and large spalls of the deck with exposed rebar. Here I want to show you, I have a couple of videos of the expansion of the deck pumping under live load that we recorded during that field inspection. So here, this will be our top flange, and this will be the bottom of the deck. So you will see this part over here hammering against that top flange. All right, then I have one more video showing the deck pumping under live load. Okay, so once we were aware of that situation, we wanted to use MIDAS to determine, first of all, why was that happening, and under which loading conditions we get that pumping of the deck. So the live load results, what it gives you is an envelope of the displacement, an envelope of the moments for your whole live load analysis. So to investigate what's actually happening with that expansion joint, we use the moving tracer tool in MIDAS. So essentially the moving tracer tool allows you to check the different results across the bridge and then determine the location of the truck and the lane loads for which that condition happens. So you can check for your maximum reaction at one of the bearings, or maximum or minimum displacement at any node, and then check what is the location of the truck and the lane loads for that condition. So once you go into the moving load tracer, again here you can select your moving load case. In this case, we were looking at displacements. So you select the node where you want the displacement check, or your maximum displacement. And then here it's the typical results for the moving load tracer. So here we have our lane loads, and then these red flags over here are showing the location of the wheel loads. Now, to this moving load tracer, it shows you the location of the truck for your maximum conditions, but it does not give you the actual displacement across the bridge under that condition. However, Midas gives you the option to use this load and write that as a static load case. So you define this loading condition as a static load case, and then rerun your analysis. So that's what we did to investigate what was happening to the joint. So we considered two cases. First case would be when a node at the midspan along that beam was having the maximum upward displacement, and this is the loading condition that we got. And then the second case would be when that same node had the maximum downward displacement. So for the first case, we have over here the load configuration for that's causing your maximum upward displacement at this node. So what's happening here is we have our truck loads concentrated in these two areas. So naturally, this will cause these two parts to move downward. And when we take a closer look at the deformed shape of the bridge, we see that this part, it's where the trucks are located, have a downward displacement, and that it's causing this deck to, or that joint to open up, and the deck to separate from the top flange. Now, once the loads are removed, or once the truck goes over the bridge, then this concrete deck will go down and start hammering the top flange. Here we have a 3D rendering of the deformed shape of the bridge. And again, here we have downward displacement where the loads are located. And on this side, we don't have any problem, because this side of the deck, it's firmly attached to the floor beam. Now on this side, since the deck has no connection to the floor beam, then obviously that you will deform like this, and you will have that gap being created. The second case, which is the more intuitive case, is the case when all your truck loads are located south of the expansion joint, and that will be the case, for example, when the truck are moving northbound, and the truck is just about to approach that expansion joint. So in that case, part of the bridge will deflect downward along with the floor beam, and since this part is not loaded, then it will stay where it is, and then creating this gap. Once the truck goes passes the expansion joint, then that gap will be closed, and again the deck will be hammering the top flange. Again, we look at the 3D rendering, and we can see the gap being created over there. In conclusion, we use different rating methods or steps for the load rating of the different components. The composite girders and the floor beams, we rated using fully the Midas composite girder module. For the non-composite floor beam, we use a spreadsheet and using the results from Midas. The main reason for that is because Midas currently doesn't perform the load rating of non-composite elements. However, it gives you the demand loads on those elements, and it also performs the design check for that. So we got the capacity of the non-composite floor beam from the Midas design module, and then from the live load analysis and the construction stage analysis, we got the demand loads on the non-composite floor beam. For the through girders, then we use a spreadsheet for the load rating. We use a spreadsheet using the demand loads results from Midas Civil. And finally, from a user's perspective, I think that the advantages of Midas Civil, it's first of all, it's a very user-friendly software. I think that the options are, at least in my opinion, I think they are very intuitive and very well located. Also, as I mentioned before, the graphic user interface, it's something that I really like about this software. It allows you to check your model and check the section properties at different stages, just to make sure that the bridge it's remodeled correctly. Also, fast and accurate bridge modeling, especially when with the bridge wizard, even a curved bridge could be modeled very, very quickly. And finally, the general section designer, that's another feature I really like about Midas. It allows you to essentially bring up any shape into your model, and not only bring that section, but it also allows you to, it also determines your section properties for you.